Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation. The paper titled, Correcting Language Model Outputs by Editing Salient Layers, proposes a novel approach for automated layer selection for model editing, known as Salient Layers Editing Model. Salient uses gradient values from a given dataset with respect to the parameters of the large language model, LLM, to create layer saliency profiles and identifies the most salient layer for editing. The process of saliency-based layer selection involves several steps. Parameter saliency. Salient computes parameter-wise saliency profiles by calculating the gradients of the loss on the editing data with respect to the trained parameters for a given example. A higher norm of the gradient indicates a greater impact of the respective parameter in making mistakes. Column saliency. Salient computes column-wise saliency profiles by averaging parameter-wise saliency values across all elements of a column in each layer's parameters of the network. This quantifies the saliency of a given column in a layer, with a higher value indicating a more significant impact on erroneous predictions. Layer saliency. To identify the saliency values for a layer, Salient further calculates averages of column-wise saliency profiles for each column in the layer and repeats this with each layer of the network. Select edit candidates. Finally, Salient selects the top K layers with the highest saliency values as candidates for model editing. Once the most salient layers are identified, model editing is performed using the MIND, Model Editor Networks with Gradient Decomposition, framework. This framework trains a lightweight model editor network to edit the weights of a specific layer. During testing, it transforms the fine-tuning gradient of the corresponding layer into a parameter update that aligns with three key properties: correctness, i.e., correcting erroneous outputs; consistency, i.e., maintaining correct outputs; and adaptiveness, i.e., adapting to semantically equivalent inputs. The model editor uses the rank, one fine-tuning gradient for the layer as input and outputs the parameter edits for that layer. This is achieved by conditioning on single-layer gradient values, reducing the computational complexity compared to editing all parameters. The overall loss to train the editor combines correctness loss and consistency loss, allowing the model editor to effectively adapt the parameters of the selected layer while maintaining correctness, consistency, and adaptiveness. The experimental work in the paper involved a series of tests to validate the effectiveness of the Salient Layers Editing Model, SALEM, compared to other models such as fine-tuning, FT, editable neural networks, ENN, knowledge editor, KE, and model editor networks with gradient decomposition, MIND. The authors used a diverse set of datasets for their experiments, including multi-NLI, dialogue NLI, empathetic dialogues, persuasion for good, fever FACTCHECKING, ZSRE, and Wikitext. These datasets cover a range of tasks such as natural language inference, dialogue understanding, emotion detection, persuasion strategy identification, fact-checking, and question answering. The performance of the models was evaluated using two key metrics: edit accuracy, EA, and drawdown, DD. EA measures the success rate of editing by evaluating how well the edited model aligns with the desired modifications or enhancements. DD measures the performance degradation of the edited model on the remaining dataset when compared to the base model. The results showed that Salem matches the edit success of MIND and ROME with considerably better computational efficiency. Salem also outperforms FT, KE, and meets MIND's results with T5, XL, and GPT-NEO. The authors also conducted layer-wise ablations to highlight the importance of selecting the most salient layer. They found that when using the sets of the 8, 9, 10E, and 9, 10, 11, MIND achieves the same performance WRTEA, which is significantly better than the other variants. This suggests that deeper layers play a more significant role in making decisions. Lastly, an error analysis revealed that for base models with low accuracy, the editing accuracy is low compared to high accuracy base models. This could be due to the absence of reliable edit samples to train the editor, which can clearly discriminate between different classes. This detailed experimental work provides a comprehensive validation of the methods proposed in the paper. This is AI Research Radar. Now, we will be delving into the next paper on our agenda. The paper titled Multimodal Healthcare AI, Identifying and Designing Clinically Relevant Vision Language Applications for Radiology, presents a comprehensive study exploring the potential applications of vision language models, VLMs, in radiology. The experimental work is divided into 3 phases: brainstorming VLM use cases, sketching VLM concepts, and user feedback sessions. In the first phase, the objective was to identify clinically relevant use cases for VLMs in radiology. This was achieved through in-depth discussions with clinical team members and brainstorming sessions with groups comprising clinical domain experts, AI researchers, and HCI researchers. The sessions were recorded, transcribed, and analyzed using affinity diagramming, interpretation sessions, and service blueprinting. The second phase aimed to translate identified use cases into design concepts for VLM applications in radiology. 4 specific use cases were selected for further development: draft report generation, augmented report review, visual search and querying, and patient imaging history highlights. Click-through prototypes for each use case were developed using Figma and validated with a radiologist team member. The final phase involved gathering feedback from a broader set of clinicians and radiologists on the perceived usefulness, acceptance, and potential concerns of the VLM concepts. Feedback sessions were conducted with 13 clinical stakeholders, and the sessions were recorded, transcribed, and analyzed using affinity diagramming. The study revealed valuable insights into the potential applications of VLMs in radiology, emphasizing the need for clinically relevant, workflow-integrated, and human-centered design. The feedback underscored the preference for AI as an assistive tool rather than a decision-making agent, suggesting a focus on lower-risk, medium-reward use cases. This experimental work validates the proposed methods by engaging directly with the end users of VLM technology in radiology, ensuring that the development of such AI applications is grounded in real-world clinical needs and practices. This is AI Research Radar. Now, we will be delving into the next paper on our agenda. The paper titled Towards Greener LLMs, Bringing Energy Efficiency to the Forefront of LLM Inference, presents a comprehensive analysis of the energy efficiency of large language models, LLMs, in data center environments. The authors delve into the trade-offs between energy efficiency and performance in LLM serving underperformance service level objectives, SLOs. The methods used in the study are as follows. Workload type. The authors define the workload type as a combination of the input and output lengths of the queries, combined with the total requests per second being sent to a model instance. They combine these levers with the only energy efficiency knob available to them in modern GPUs at a node level: frequency scaling. Impact of workload type. The workload is divided into buckets based on the input and output length and number of tokens. Both input and output lengths are divided into 3 buckets: small, medium, and large. A streaming workload is run through the model instance to observe the impact on latency, throughput, and energy. Impact of parallelism. The authors vary the tensor parallelism degree across different number of GPUs under medium load and medium input-output workload types. They use tensor parallelism degrees of 2, 4, and 8 within a single DGX H100 node, and name these configurations TP2, TP4, and TP8. The impact on latency, throughput, and energy is observed. Impact of batching. The maximum allowed batch size is increased and the patterns in performance and energy with frequency scaling are observed. The impact on latency, throughput, and energy is observed. Characterization of LLM inference environments. A thorough characterization of energy consumption in LLM inference environments under various settings is performed. The goal of the characterization is to generate datasets that can provide insights and guide the design of future energy management frameworks specifically designed for LLM inference servers. Analysis of available knobs to LLM inference servers. The available knobs to LLM inference servers and their impact on the performance energy trade-off are analyzed. The impact of these knobs on the latency, throughput, as well as the energy is characterized. Requirements for an energy-efficient LLM inference framework. The authors outline the requirements for an energy-efficient LLM inference framework. They propose strategies that accommodate the dynamic and heterogeneous nature of workload characteristics, ensuring that computational resources are efficiently utilized in response to evolving workload demands. This detailed analysis provides a comprehensive understanding of the energy efficiency of LLMs in data center environments. Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.